Hello everyone, my name is Andrea McIntyre, and in this presentation we will be going over system considerations for monitors and high cell count industrial applications. We will start off by covering some examples of high cell count applications and possible battery chemistries for them. We will particularly focus on lithium-ion batteries, discussing their popularity and the protections needed to implement them in a high cell count system. Along with this, we will also cover the differences between protectors, monitors, and gauges, and the uses for each of these devices. Next, we'll move on to cell balancing, determining what it is and why it is important. After this, we will dive into advanced battery packs. In this section, we'll see gauges and monitors being implemented into example systems, and we'll also go over some considerations pertaining to these systems, such as high and low side FET configurations. Finally, we'll discuss device stacking for systems where a single chip solution is just not enough. Currently, there are a growing number of applications that require higher battery power than a typical phone or laptop. To meet their power needs, these applications use a combination of cells and chemistries to create higher voltage and higher current battery packs. Some common examples of high cell count applications are shown here on this slide, with higher cell counts to the left and lower cell counts to the right. Although the cell chemistries in each of these applications differ, each needs monitoring and protection. Many high cell count applications choose lithium-ion batteries, and it is the most common battery chemistry for a variety of applications. Other chemistries, such as lead acid, are still used for some applications, like in your car as a car battery to help start your engine. But since they were introduced in 1991, lithium-ion batteries have become the most popular due to their cost-effectiveness, high cycle life, low self-discharge, and high energy density. Digging deeper, it's important to note that there are several chemistries of lithium-ion batteries, each with their own strengths and applications. The differences between chemistries can be highlighted by examining two lithium and lithium-ion batteries. The first, nickel manganese cobalt oxide, or NMC, and then the second is lithium iron phosphate, or LFP. NMC batteries have a high energy density, making them ideal for applications like power tools that need a small but powerful battery that can operate for long periods of time with few charges. LFP batteries, on the other hand, have a lower energy density, so a slightly larger battery is needed to maintain the same energy as other lithium and lithium-ion batteries. But they have a higher thermal stability than other lithium-ion batteries. This means that LFP batteries can withstand high voltages for long periods of time with a lower risk for thermal runaway and fire. This makes them great for energy storage systems where battery size isn't as much of a consideration, but safety and thermal stability is. It's important to remember through this discussion, though, that although the chemistries each have their own unique identity, all lithium and lithium-ion batteries require monitoring and protection to ensure they perform safely and effectively. In order to perform safely and effectively, lithium-ion batteries need to operate within a specific range of conditions, and the protection circuitry of a battery management system helps the battery stay in that range. As we just stated, lithium-ion batteries require monitoring and protection, and there are standards in place, like those highlighted on this slide, that detail these protections. Some simple batteries only need basic overvoltage protection, but other batteries may require additional features like undervoltage, current, or temperature protections. Some batteries may even call for independent primary and secondary protectors. We will cover these protections further in the coming slides. Before we do that, though, we will look at the three classes of devices that will be offering the protections for lithium-ion battery packs. Although the lines between these devices can be fuzzy, there are three major categories. Protectors, the top box, offer the lowest complexity for simple pack designs. They provide cost-effective and hardware-based solutions that address unsafe conditions. Monitors, shown in the middle box, offer the highest flexibility. They have more advanced protections than protectors, and the pack designer is able to write code that is specific to their system needs. Gauge ICs, shown last in the bottom dark blue box, are the most highly integrated of the three. They feature high accuracy state of charge information and a faster development time since the firmware is included. But because they have integrated firmware, gauges have less flexibility than monitors. Alright, now let's jump into the protections. The most basic is overvoltage. So, why is overvoltage protection important? Well, for lithium-ion batteries, charging above their rated voltage can cause lithium plating, which reduces the battery capacity due to a reduction in free lithium ions. There is also the possibility of dendrites forming in the battery, potentially causing a short between the electrodes. If you look at the figure to the right over here, you can see how the BQ7718 protector provides overvoltage protection. It monitors cell voltage for each cell in the stack and can either blow a fuse, up here, or send an overvoltage signal to the system if the overvoltage threshold is crossed. Okay, now let's see how we can expand overvoltage protection into a higher cell count system. So here's a reference design that uses the BQ7718 from last slide, but this reference design demonstrates the 7718 stacking ability as well as its protection features. Since the 7718 can only support up to 5 series cells per device, 3 devices are needed to protect the system. Thanks to the logic of this circuit, if any one of the 7718s detects an overvoltage condition in a cell, after a set delay time, they will turn on this N-channel MOSFET right here and blow the fuse by pulling this third leg to ground. Blowing the fuse severs the connection between the battery over here and the charger right here, and it prevents the battery pack from overcharging. So as a quick aside, the TIDA 00108 reference design that we saw on the previous slide is an official TI reference design. Anytime you see one of these TIDA numbers, you can do a quick search and you will find a complete design guide, schematic, and all the board files needed to build this particular reference design. This will be true for all of the TI reference design numbers we refer to in this presentation, so make sure to keep an eye out. Alright, back to protections. The next most common cell protection is undervoltage. Again, why is this important? Well, if lithium-ion batteries are over-discharged or stored for extended periods of time at too low of a voltage, they can have a breakdown of the electrode materials. Due to this, monitoring of the individual cell voltage is needed. And when the cell undervoltage is reached, the discharge vent needs to open, preventing discharge of the battery. Because the cell undervoltage threshold varies depending on cell chemistry, it is important to check the cell's datasheet to determine an appropriate undervoltage threshold. Next up is temperature. As I'm sure many of you know, lithium-ion batteries are complex chemical systems and are consequently sensitive to temperature. Both low and high temperatures can cause problems. Cold temperatures are problematic because they reduce the current carrying capability and effective capacity of the cell, thus making lithium plating more likely. JIDA standards recommend not charging lithium-ion batteries below 0 degrees Celsius to avoid these adverse effects. For high temperatures, there are problems too, including the possibility of thermal runaway, which can lead to fire. Again, JIDA offers the recommendation of reducing charge current above temperatures of 45 degrees Celsius. So, how do we collect and analyze temperature since we know how important this data is for battery protection? Well, temperature can be measured by the protector, which senses the voltage at a pin connected to a thermistor. The thermistor is placed in the system where the temperatures may become critically hot or cold, such as near the battery pack. The protector, or a monitor, can monitor the voltage across the thermistor and then calculate the temperature and take action if one of the protection thresholds is met. So now we will look at some protectors that offer voltage and temperature protections. The BQ772XX family shown on the slide provides overvoltage, undervoltage, overtemperature, and open wire protections, but no current protections. The BQ77216 in the image to the right is designed to be used for high cell counts, up to 16 series cells, and can be used as a secondary protector. Later in the presentation, I will show a reference design with the 77216, and you can have a better look at what it means when I say the 77216 is a secondary protector. As for the 77207, it has the same functionality as the 77216, but is designed for a lower cell count, 3 to 7 series cells. If a fault is detected in either the 77207 or the 77216, the protector's internal delay timer initiates, and once that expires, the protector will open either one or both of the FETs depending on the fault. This will prevent the battery from either charging, discharging, or both. In addition to FET control and an internal delay timer, some other features that makes this family of protectors very attractive are their high accuracy and overvoltage protection as well as low power consumption. We've talked about the importance of voltage and temperature protections, but protection is also needed for excessive currents. There are several conditions that can lead to high currents. First, if packed terminals become exposed, they can short together. To address this, we need short circuit and discharge protection. Second, loads attached to the battery may draw too much current, so we may need overcurrent and discharge protection. And finally, if an unapproved charger is used, it may allow high currents when charging. Having overcurrent and charge protection will prevent high charging current from damaging the system. In order to sense the current, the device uses a low resistance sense resistor that's shown in the figure to the right here. The device measures the voltage drop from the positive and negative terminals of the sense resistor while current is flowing to determine both the magnitude and direction of the current. This information is used by the device for current measurement in order to disable the charge and discharge FETs when a current fault occurs. So here's an example that implements all the protections that we've talked about thus far. The BQ77905 and the BQ77915 both have protections that can address undervoltage, 2 different levels of overcurrent and discharge, and short circuiting. These devices also include over and under temperature protections in both charge and discharge modes. Without even looking at this list, however, we can get a general idea of this system's protections by looking at this image on the left. You can see the sense resistor for current measurements, right here, and the thermistor for temperature readings, right here, as well as the fuse and charge and discharge FETs for opening the circuit or preventing charge or discharge. And here's the charge and discharge FETs here, and we have our fuse up here. If you're looking for a battery management system that offers a myriad of protections but isn't as complex as a monitor, this protector is a great choice. As a quick note, if you're wondering whether to choose the 905 or the 915, know that the 915 has cell balancing, but the 905 does not. We'll see an example of the 915 cell balancing later. So moving on from protections, we will now look at cell balancing. So, why is cell balancing important? Why do we need it in a system? Well, lithium-ion batteries are greatly impacted by the proper management of the charge and discharge cycle of the cells. Charging and recharging lithium-ion batteries over and over again causes a variation in voltage, capacity, and internal impedance in the individual cells, and this can lead to faster rates of degradation and lower overall battery pack efficiency if it's not addressed. It's not a matter of if cells will become imbalanced, it's a when. And if there's no monitoring or balancing system in place, these cells can be pushed into an undesirable voltage range, ultimately damaging them. Think of a battery pack like a chain, with each cell being a link in that chain. Like a chain, the battery pack is only as strong as its weakest link or cell. The image on the left shows an illustration of this. Although cell 1 and 3 have charge left, as we can see here and here, because cell 2 is fully discharged, that charge in cell 1 and in cell 3 will remain unused. In the example right next to this, you can see the opposite problem. Cell 2 is fully charged, but cell 1 and cell 3 could still use more charging. That won't happen though. Cell 1 and cell 3 won't be charged more because overvoltage protections will prevent the overcharging of cell 2, and that will also stop the charging of cell 1 and cell 3. So this leads to a reduction in runtime of the battery pack. So what happens if instead of stopping charging on 2 if it's going into overvoltage, what if we just force it in order to charge 1 and 3 a little bit more to avoid that reduction in runtime? Well, looking at the graph on the right will tell you the answer. So over its lifetime, overcharging a 4.2 volt cell by even 150 millivolts leads to a reduction in both cell capacity and the number of cycles by approximately half. So if we go from 4.2 to 4.35, the number of cycles goes from around 500 to 250, and then the cell capacity goes from probably about 800 to 0. So that is a very drastic difference. So now that we've seen how detrimental a lack of cell balancing can be, let's see what cell balancing entails and how it looks in the system. In the system to the left, cell balancing prevents any of the cells from being charged above a set voltage. If any of the individual cell charges rises above this voltage, internal balancing FETs for those overcharged cells turn on and divert current through these resistors, dissipating charge for just the overcharged cells. So the FETs are in between each of these pins, and these are the resistors that the charge is going to be dissipated over. So when this FET gets turned on, it creates a loop. So this charge is going to come down, it's going to go through this resistor, dissipating some power, going to go through the FET, go through, dissipate more power, and it's going to completely bypass this battery. So this allows the cells that haven't reached a voltage threshold yet to continue charging until all the cells are balanced. What's shown here is an example of simple, passive, and voltage-based balancing, which may be included in a protector IC. But more advanced balancing algorithms are available that would require a battery monitor. One important note is that the balancing current can be adjusted with the resistor of the filter circuit. Increasing the resistor value decreases the internal balancing current, but it increases the filter effectiveness. Just as decreasing the resistor value increases the balancing current, but it decreases the filter effectiveness. If the desired cell balancing current is less than 50 milliamps, balancing will be handled by the internal balancing FETs of the device. But you can also use external balancing FETs if you need a higher cell balancing current or better filtering. Due to complexity, though, I won't cover external FET configurations right now, but you can read about cell balancing in the BQ77915 datasheet available on TI.com if you'd like to know more and see some examples of external balancing FET configurations. Up until now, we've only discussed protectors and seen them providing primary protections, but they can also provide secondary protection in a system where a monitor or a gauge is providing primary protections. So let's look at these new devices. First, although gauges can be a great option for some systems, in this presentation, we're going to focus more on monitors. Monitors are great because they offer flexibility for protection thresholds and timings, and they can also measure current, temperature, and individual cell voltages. They can then send these measurements to a microcontroller that can make decisions based on this information, such as enabling and disabling protection FETs or balancing cells. So here's an example of a system that uses a monitor. The monitor shown here is the BQ76920, and it can be paired with a microcontroller or a gauge. The BQ769X0 monitor family has devices for up to 5, 10, and 15 cell batteries, and can control low-side charge and discharge N-channel MOSFETs. 769X0 devices contain ADCs, meaning they digitize the analog voltage, current, and temperature data that they collect. All this digital data can be sent back to the microcontroller using I2C communication. Pack designers using this family of devices will also have a lot of flexibility and can customize aspects of the device such as protection thresholds and delay timings to their liking. Okay, so switching gears a little bit, hopefully everyone noted those low-side N-channel MOSFETs in the last slide because we're going to learn more about them now. Charge and discharge FETs, like those in the last slide, are configured one of two ways in a system, either low-side or high-side, and our two most popular monitor families each use a different FET configuration. The BQ769X0 family, as you have already seen, uses low-side FETs, and the newest monitor family, the BQ769X2, which you will be seeing more of in later slides, uses high-side FETs. So, what's the difference? High-side FETs allow for continuous communication between the microcontroller and monitor even when the FETs are off by preserving the monitor's ground connection to the pack. Essentially, the pack, microcontroller, and monitor all share a common ground. This configuration does require the FET gate voltage to be higher than the top of stack battery voltage for the FETs to turn on, but the 769X2 family has high-side N-channel MOSFET drivers with an integrated charge pump to achieve this. Low-side FET configurations, on the other hand, cannot maintain the common ground between pack, microcontroller, and monitor when the FETs are off, thus preventing continuous communication. Despite this, some system specifications include an isolated interface or require low-side switching, so the 769X0 family, which has integrated low-side FET drivers, is great for these applications. So here's a TI reference design using the BQ76930. This member of the 769X0 family can monitor 10 cells in series and is paired here with the MSP430 microcontroller for communication and protection. If you look closely at the bottom of this reference design, I'll circle it here, you'll see the two low-side charge and discharge FETs I elaborated upon in the last slide. Additionally, the product folder for this monitor on TI.com contains sample code to provide an example of how to communicate between monitor and microcontroller. So go ahead and check that out if you're interested. And here is the newest member of TI's battery monitor family. As we've discussed, the BQ769X2 utilizes the integrated charge pump and high-side FET drivers to allow for high-side N-channel MOSFETs. This eliminates the need for an extra IC, helping customers simplify designs and save time while sourcing parts. This monitor also has two independent ADCs that allow for high measurement accuracy and simultaneous sampling of voltage and current, as well as options for either autonomous or host-controlled cell balancing. Additionally, the 769X2 family can provide protections for a myriad of current, voltage, and temperature conditions listed here, and choose to blow a fuse or open FETs if any of the protection thresholds are crossed. Finally, the 769X2 family can be implemented with pre-charge and pre-discharge FETs. These FETs are enabled during FET turn-on to either limit inrush current during discharge or reduce charge current during charging. We will see an implementation of this on the next slide. So here's a reference design showing a system using the BQ769X2 battery monitor that we just covered. Note the high-side FETs and also the pre-discharge FET to limit inrush current during FET turn-on. So let's take a closer look at how these FETs work together. When a signal is sent to turn on the discharge FET, which is right here, the pre-discharge FET, which is right here, will turn on first. Current then flows through the pre-discharge FET and this resistor, reducing the inrush current. And then the regular FET turns on after a set delay. When the discharge FET turns on, the current is within a safe range for this FET because the inrush current has already been limited by the pre-discharge FET path that has this resistor right here. After the discharge FET turns on, the pre-discharge FET then turns off so that less power is dissipated while the system is functioning normally. This reference design also includes a microcontroller to control the BQ769X2 battery monitor and a BQ77216 secondary protector, which works with the monitor using OR logic, shown here in this circuitry, to blow a fuse in the case of a fault. That means that if either the 77216 or the 769X2 detects a fault, either one of these can take action to blow this fuse. So overall, this system is designed for a 10 to 16 series cell battery pack, and it is also geared towards saving energy to allow for longer shipping and idle times. So now we'll take a look at gauging. Gauges are able to provide many complex features to the user, but they have limited flexibility. Some of these features include providing an estimate of the remaining charge in the battery during use and the present battery charge during charging. A few gauges are even able to provide information about the state of health of the battery and record lifetime data. They can also be a black box recorder to inspect what happened after a permanent fail event. While gauges do offer many advanced features, the firmware is fixed, so there is a trade-off between integration and flexibility when you're choosing a gauge. We won't be covering gauges in too much depth in this presentation, but these slides are available in PDF format for more consideration if you'd like to learn more. The main takeaway, though, is that TI offers different gauge types for different system topologies, so you should be able to find a suitable device that meets your needs. Additionally, TI has a gauge that can be paired with a monitor. The BQ78350 can be implemented in a system with the BQ769X0 monitor family. And there are also top-of-stack gauges available for higher cell counts. So leaving gauges, we'll finish this presentation with some stacking implementations. Stacking is necessary because, for some batteries, a single-chip solution may not be available for the cell count needed. In this case, it may be necessary to stack multiple devices to achieve the desired cell count. One of our amazing systems engineers, Terry, has a presentation that covers this topic in more depth, and I have attached the link to it on this slide. In the first stacking example, we have a TI reference design using the BQ76930 battery monitor. This design is pretty popular and can accommodate 20 series cells. The microcontroller in this system is able to communicate with both battery monitors by using an isolator to interface with the upper device. Here's the isolator here. It's the ISO 1541. Additionally, since both monitors need to provide protection, the FET control needs to be combined. To do this, OR logic is used so that the FETs can be turned off if a fault is detected by either monitor. So as you can see, you have both of these monitors, and this OR logic is here that takes input from both monitors so both are able to control the FETs. This design can also be scaled up to use the BQ76940, which would allow for 30 cells in series. The second and final stacking design I will show you today utilizes two BQ76952 monitors to achieve a 32 series cell solution. This design is also pretty popular as it uses our newest monitor and can accommodate a large number of cells. From this image from the technical article, you can see that this solution uses low side FETs instead of the usual high side. See the low side here? And therefore utilizes low side gate drivers for the charge and discharge FETs to overcome the gate capacitance of these FETs. This system uses OR logic to control the FETs in the same way that the design in the last slide does as well. Wrapping up, there's several key points I would like to emphasize. First, high cell count lithium batteries are attractive due to their high energy density, but they require monitoring and protection to ensure their safety and efficacy. Second, more advanced battery packs may need additional features depending on the system application and customer needs. Some of these features include cell balancing to preserve battery health and high side FET drive to allow for communications while the protections are triggered. Third, stacking may be necessary for very high cell count batteries. Sometimes a single chip solution does not exist, and using multiple of the same component is the best option. And finally, if anyone would like to see examples of the devices in this presentation integrated into a system, take a look at our TI reference designs. I will include the links to the reference designs covered in this presentation in this slide. Thank you all for your time, and I hope you found this presentation informative.